some stuff. So the we're going back to the interpretations to do with quantum mechanics, and I originally delayed doing the interpretations because I wanted to make sure to be able to cover special relativity. Right, it's something that is very doable with a grade 12 high school level math and physics interpretations and so on. And the quantum interpretations are a little bit more like, let's just say the physicists in the world, a lot of physicists in the world don't care about the interpretations as much as they care about the math that works, right? The theory and the math and the predictions it can make, and any new inventions, anything you predict with quantum mechanics works. So some people don't really pay attention to the interpretations as much, but of course, fundamentally, the idea of like what the heck's going on is probably actually pretty important too. So it's good that we're getting to look at that as well. I'm just going to show you quick here what we could have done if we had time and if we were in class and so on. The h-bar proportionality thing that Max Planck found between energy and the minimum energy you can have and the frequency of light. That h-bar constant, that was a very, very, very big surprise that it was needed. But remember, it explained the ultraviolet catastrophe and other things since, right? It keeps coming up in more and more discoveries through the momentum of light and everything, right? So we can actually measure that in class. It's actually surprisingly easy to do. So what you do is we know that energy is to do with voltage, and the frequency is to do with color, right? And so you actually use little LEDs. So there's actually an inside of there's a small LED. So somewhere in here, it'll probably show the idea. Like you have a little LED, and you have just a 6-volt battery or a 9-volt battery we were going to use. And this is a potentiometer, which is just a resistor and a variable resistor. And so you can adjust the resistance to allow some voltage to start to go across the LED. And you increase that voltage slowly, 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 while you look through a black tube, because you want to see what they call first light. You want to see when light just starts to get emitted by that LED. Because then what you've got is, the frequency, because it's a blue or a red or a yellow or a green or whatever, right? So that's the frequency and wavelength of the light. And then the energy that corresponds with that frequency is the voltage across the LED. So you can see here the voltmeter literally just goes across the LED to know how much voltage is there. So the way it works, of course, is like I said, the voltage applied across the LED is the energy that's being given to the electrons to be converted to photons, and we know that the energy goes h bar f. So if we know the energy, we know the frequency, we can graph energy and frequency for a bunch of different frequencies and corresponding energies. The slope ends up being h bar. That's how easy this actually is. It's just, you just watch for what voltage for the first light to be produced, and you graph it. So you end up graphing energy versus frequency. This graph looks a little bit better. The axes are spread out so you can actually see the slope. But you just select all and right click and add a trend line and measure the slope. Look at the slope, 6.658 times 10 to the negative 34. H bar, that's what we got from actual measurements due to the voltages for first light. H bar, remember, was 6.63 times 10 to the negative 34. So yeah, it's just amazing. To me, it's just amazing that we can actually measure that. Maybe what's more amazing is that I never saw it in my schooling and in years of teaching. Like, I just came across it, like I said, in a little workshop where someone mentioned, how you can measure H bar? Like, what if we did, it was relating it to something else. And so I was like, hang on, back up the truck. What? You can measure H bar? And so, like I said, I've been excited about it and doing it ever since, because it just seems kind of neat that we can actually do it. So that's just a quick little, I just wanted to show you it's a very concrete number that we can actually measure. I think back in the day for me, LEDs certainly weren't as available. Maybe potentiometers, would say probably are, because that doesn't look exactly modern, does it? But the LEDs and so on are maybe a little bit more available now than they were. Anyways, so here we go. Interpretations of quantum theory. And then what's the last part here? The Copenhagen interpretation a little bit more and some weird observation effects. But we are going to end up having an overall feeling, understanding for how the standard model, as we've talked about it. Remember, we talked about the standard model says there's the weak force and the strong force and the electromagnetic force and the gravity force, and there's equations to do with each of the forces, and there's exchange particles and all this stuff. So we're going to try and make sense of where all that came from. So to start out, and we'll lead towards that eventually here, I want to look at the weird concept here about how a single particle can go through two slits at a time, because we see it happening. And so, try and make sense of that, of course, is what we're trying to do here. I don't have my file names for the videos here. Let's try just clicking on the link, see if it still works. As usual, eh? All right, so let's go. It's Dr. Quantum, I believe it is actually called in the name. So let's go to my videos. Dr. Quantum. Dr. Quantum double slit experiment. And we want to go to 245, maybe. If the timestamps are the same on the file as they are at the web page.
And here we are, the granddaddy of all quantum weirdness. The infamous double
here we go.
Create an interference pattern like a wave. It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potential.
The idea of what's actually happening is what we're talking about a lot today, right? So he's saying it becomes a wave of potential, whatever the heck that means.
Goes through both slits and interferes with itself to hit the wall like a particle.
I'm surprised you didn't mix the word momentum into that, and its momentums cancel, and so, makes it sound official, right?
But mathematically, it's even stranger. It goes through both slits and it goes through neither.
So this is some of the interpretations we're going to see.
And it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other.
You'll hear that lingo. All these possibilities are in superposition. That's the Copenhagen interpretation we'll talk about.
But physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through.
So I'm gonna show you results of an experiment that we can do in room 124 where we do this. We actually look to see which slit the photons go through. Okay, you'll see the rundown of it. And guess what happens here? If the particle can't go through both slits, because you look to see which one it went through. Spoiler alert here, but the double slit interference pattern disappears just by knowing which one it goes through. The double slit pattern disappears, and you're going to see that a video of it from me doing that in room 124.
Put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands.
Which is not correct. He says produce a pattern of two bands. No, it would produce a single slit interference pattern, right? This would be actually a single slit interference pattern rather than the double slit interference pattern.
Bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one.
That's the weirdest part about quantum mechanics in my mind, is that if you observe, it affects the results.
Not both. The electron decided to act differently. As though it was aware it was being watched. And it was here that physicists stepped forever into the strange netherworld of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this?
Like, why does observing affect anything? What constitutes an observer? It can be just detectors and so on.
The observer collapsed the wave function simply by observing.
So the collapsed the wave function is the lingo they use in one of the interpretations. We talked already about Schrodinger's wave equations, and the wave equations would say that the electron could be at either spot, be able to go through either slit. And if you observe, it collapses those wave possibilities down to just the one slit. And so you get a single slit interference pattern. Challenge of quantum reality. This one probably actually works fine. It's the Perimeter Institute. They have no need to change.
Physicists have developed.
And we're looking at, it says the first 8 minutes, but then it says 1945. Oh.
Developed a number of mental pictures of what's happening, but there's no agreement about which one's right.
We're talking about the number of mental pictures about what's actually going on, but no one agrees. No one knows which is right, basically.
There's something called the collapse interpretation. The idea is that there's only a wave that passes through the slits, and then the wave, when it arrives at the screen, it collapses, so it's only detected in one of the many possible places it can be detected at the screen.
It seems to behave as a wave in between the source and detector, so it can go around these barriers and go both ways through the slits.
You'll say the electrons, any quantum particles for that matter, even buckyballs, they travel as a wave and arrive as a particle. Now, that's the wave-particle duality in a nutshell in terms of what we're observing. But how the heck does that make sense, right? Like, it's all weird.
The pilot wave interpretation says that electrons are real particles, like tiny, tiny tennis balls, guided by an unseen wave.
In this case, you can explain why the particle is only detected in one place behind the slits, because there's only one particle.
It's this pilot wave that tells the electron what to do. So the pilot wave mysteriously knows about everything, where everything is in the universe, and it feels whether or not there's a one slit or two slits, or one slit open or the other slit open. And it can somehow tell the electron about this and move it around and get it to go different places.
To me, that's probably been my favorite interpretation, the pilot wave, because you could picture the particle moving through space-time having, effects based on there being one slit or two. And so the particle is just riding waves essentially through space-time. I don't know why it's not said like that more often. To me, that kind of makes the most sense. But I don't know. You don't even have to close the. I don't think you have to close the second slit. You just have to observe. So that's kind of weird. But...
If wave-guided particles aren't your thing, how about parallel universes?
One that doesn't make any sense to me, but lots of people like it. But parallel universes, here we go.
The many worlds interpretation explains the double slit experiment by saying that parallel universes are being created all the time.
So in quantum mechanics, we have superposition of different states, and the many world interpretation says that all these different superposition of states are equally real.
The world literally splits into many copies, and so we only see one thing happening, but there are people in another parallel world who see another thing happening.
There's actually reasons for people to say this, by the way. This isn't just nonsense that someone says for fun. We'll see soon the Schrodinger's cat analogy and so on. But basically, the quantum world behaves as if both of those realities exist until we look to see which one happened. And then one of them collapses out of existence, and then the other one becomes the reality you're observing. So the interpretation from that is like, okay, both of those realities exist. It's just we end up in one of them. So the other ones actually still exist. weird, but.
While some researchers attempt to construct mental images of the quantum world, others think this world can't be pictured. The Copenhagen interpretation says that we should focus only on the results of measurements in quantum experiments.
When an experimenter enters a lab and interacts with a quantum mechanical system, the Copenhagen interpretation says don't ignore that interaction. It's a crucial piece of what's happening.
It's very powerful to restrict yourself to questions about what we can see. It's very powerful to restrict yourself to questions about what we actually do, because that teaches you to think about the experiment in a very honest way, in a way that appeals directly to the experiment itself without
showing the wave of potentials as to where the particle could be as like smoke for some reason there, and then it condenses to a spot.
invoking extra theoretical ideas.
In the double slit experiment with electrons or with photons or with buckyballs or anything, the question is what happens between the source, the double slit, and the screen. John Archibald Wheeler, famous American physicist, said, "This is just a smoky dragon," meaning that we cannot talk about it. We can mathematically describe it, but it is impossible to make a picture.
I think none of these philosophical discussions bear fruit. The only thing that bears fruit are the calculations.
There's no consensus about which interpretation is right, but they all predict the same results for all experiments.
We really do know what's going on at the subatomic level. We have a complete and accurate mathematical description of what happens.
That mathematical description is something everyone agrees on. It allows us to make incredibly accurate predictions, and that's very useful.
Something that people didn't anticipate is that if you have a weird version of reality, then you can make that weird version of reality do some work for you.
Do some work for you? That's weird.
How can quantum work for us if we don't even know what's going on?
We know what's happening. We just don't know why.
If we can't measure a quantum object without disturbing it, what can we possibly make?
Plenty.
Quantum physics is invading everyday life, even if we're not aware of it. And so as the world becomes increasingly more technology-oriented, we're just going to see a world that is increasingly quantum physics-oriented.
Many technologies take advantage of the wave behavior of electrons. One of them is the electron microscope. An electron with a large momentum has a wavelength much smaller than visible light. So scientists use electron microscopes to resolve objects down to the level of individual atoms. We can look at strands of DNA, examine viruses, and design nanotechnologies. The particle nature of light is at the heart of a range of everyday technologies.
So that electron microscope works based on something we talked about previously called the quantum tunneling. And so if you picture, a surface, the details of a surface, and you're scanning, let's see what something looks like, or maybe it's the molecule of the DNA or something sitting here, right? So it could be a molecule of DNA sitting there. You've got the electron microscope probe, and then you've got electrons that are, sort of loosely attached to here, and electrons loosely attached to there. The number of electrons that quantum tunnel over to the probe and then are registered as a current in the system and a blip on the screen, meaning the distance from here was sort of known. What turns out to be true is the distance to here and then to here and then to here and then whatever, like all these different distances, the number of electrons that quantum tunnel is extremely sensitive to that distance. And so it gives you that ability to scan and get an image of what that distance is. So it allows you to look at, essentially, get information about the shape of things. And it's based on quantum tunneling. And quantum tunneling, again, is like this electron has wave properties, and it could be, the electron could be here, or it could be here, or it could be here. There's certain possible spots where this electron could be. And so every once in a while, it appears there and ends up being registered on this electron microscope probe, electrode tip, whatever. It's a pretty simple idea, and they said, oh, let's try this, and it worked amazingly. So the electron microscopes are fantastic. Yeah.
Technologies. Traffic lights, solar panels, barcode scanners, and remote controls are all devices that incorporate quantum effects related to photons.
So the solar panel is easy to understand. It's the photoelectric effect. Energy landing on the solar panel kicks off electrons. Those electrons go through a circuit, provide energy to charge batteries and so on. It's just the photoelectric effect.
Inside modern devices for information processing, like CD players, cellular phone, computers, there are, at the brain itself, there's an element called a transistor. And the transistor would not work today if we would not have the laws of quantum mechanics.
We can control the flow of electricity. We can amplify it, we can turn it off, we can turn it on. Our ability to turn things on and off, control the flow, gave us logic gates. Those logic gates, when we were able to replicate them on a mass scale through commercialization of that discovery, led to integrated circuits. Integrated circuits led to computers. Computers led to the information age and the internet.
If you do not think quantum mechanics is important,
the heart of computers is a junction between two different metalloids, and they call it a PN junction. So call it a PN junction, and then there's roughly speaking, the quantum version of it anyways, the electron has a possibility of being in multiple spots. And so sometimes it ends up on the other side, in which case you're registering a current, and then it's, the amount of voltage that's on here changes the properties of how the electrons jump from one to the other, and so on. So, but it does have to do with the quantum properties as well. And this PN junction stuff, they refer to the spot that the electron has a chance of going to as holes. And so there's electrons on one side and there's holes on the other. And then as the electron jumps into these other holes based on its quantum properties, that's the heart of computers. That's the heart of transistors, and like you said, and then integrated circuits and so on. But computers essentially in a basic level are a bunch of switches that are like yes, no. And so if this is true, then this, and so on. And it's these Boolean logic gates that are all chained together to create the modern computer. It's mind-boggling that it works and so on. But it's pretty cool. Where am I going here?
Important, and you do not like quantum mechanics, you can choose to live your life without.
Like if you can refuse to believe quantum mechanics if you want, I'm going to live my life without quantum mechanics because I don't like it. I don't believe it. I don't think God should play dice with the universe, blah, blah, blah.
Please get rid of your cell phone, your iPod, your computer, all electronic equipment, and then you can live your life without quantum mechanics.
I had no idea my phone was quantum.
No one knew the range of technologies possible when the theories were first presented 100 years ago. But our knowledge developed over decades.
There were naysayers. Like, why are we giving funding to blah, blah, whatever university and so on to these experiments? Why are we giving funding to that? It's a waste of money. What are you wasting your time for? And then eventually it's like, oh, wait, we invented cell phones and we invented computers and we invented GPS and we invented, unforeseen advances in science because of science itself.
Quantum mechanics has revolutionized the way we live our life. The development of the technology and applications enables more science to be done. As more science is done, more technology and more applications are developed.
At the Institute for Quantum Computing in Waterloo, Ontario, researchers are developing a range of new quantum technologies. Quantum cryptography takes advantage of the concept of measurement disturbance. It's the basis of ultra-secure secret codes that are starting to be used by banks and governments to safeguard highly sensitive information.
In quantum physics, when you make a measurement, it doesn't tell you everything about the system you're looking at. And further, just by looking at the system, you change it. In cryptography, we can use this to detect eavesdroppers. So not only can an eavesdropper not get all the information about a system, but will inevitably change the signal and can be detected. So it's quite clever, actually.
Researchers are also using quantum physics to build a new breed of ultra-powerful computers.
So the idea of a quantum computer is, suppose you built a computer out of individual atoms or other very small objects that were behaving quantum mechanically.
then instead of just having one number in its memory and doing computations on that one number to get an answer, it could have, in some sense, many numbers at the same time and do computations on all of them. And so consequently could solve some problems much faster than any regular computer.
In the case of quantum computing and quantum cryptography, we go much deeper in the quantum world, much kind of places where we don't only put our big toe in the ocean of the quantum world, but really go and swim in it.
And what's really exciting is that we can't even imagine the kinds of discoveries that our future physicists are going to make. But what we know is that they're going to absolutely transform society.
You know, history shows that it will be transformative for sure. So what do we got here? So yeah, so there's many interpretations, right, about quantum mechanics, and we're going to talk about each one a little bit. But all these interpretations basically, you know, give the same mathematical prediction. So there's absolutely no way to test them, and so there really is a chance it's like, okay, this is really just philosophy at that point, not really science, right? So these many interpretations exist, but you know, all of the experimental results just agree over the last 40, probably 60 years now. Yeah, we're not actually explaining anything when we talk about these interpretations, but it's neat to think about it. So the pilot wave interpretation was mentioned, where it's like, these are really particles. Everything's okay, everybody, just relax. They're really particles, but they're guided by a wave of potential of where they can possibly be. Those are Schrodinger's wave equations, right? This is just a theory. I'm not saying it's true. I'm just saying, you know, if it is, then everybody can relax. Particles are just particles. That's all. It's all. Everything's all good. But they're guided as you know, by wave properties through space-time. So the interference patterns just results from the waves telling the particle where or where not to land based on constructive and destructive interference. Pretty beautiful idea, really, I kind of think. It doesn't explain everything, though, mind you. The many world interpretation is the idea that the electron can go through either one slit or the other. In it, it actually goes through both, and if you observe it going through one, that's the, you know, you're in that universe, and then the other universe still exists, right? It also goes through the other slit in a different universe. So basically, universes split off, entire universes split off every time there's a random chance of something happening. So infinite universes just constantly splitting off. I personally find that kind of ridiculous. Where's all that energy coming from, right? So question marks on that one in my mind. The transactional interpretation, it's kind of neat. So for ages, like I said, physicists were ignoring that that negative answer. So you have the magnitude of the Schrodinger's wave equations squared gives you the probability, right? So you take the root of the square of it and you get plus or minus answers, and everybody's like, well, mathematically, of course, we're not talking about the negative one because that would mean going backwards in time, right? So eventually someone said, well, wait a minute, maybe going backwards in time would be useful. So quantum entanglement would be to do with, like, two electrons can be quantum entangled. And let's say an electron has a chance of having a spin this way or a spin this way, okay? And these electrons are entangled. And so until you actually look and see what spin they have, and you could literally think of it as an electron spinning if you want, but it's actually just a word to help us remember what that we're referring to something. But so over here, this one could have, again, same thing, right? One or the other. And so it's not until you actually observe which one. And so if you observe and then this one has this, guaranteed instantly on the other side of the universe, if someone looked, this one would also have that spin, okay? Or if you looked and it had the other spin. So the idea of quantum entanglement is that, you know, across an infinite distance, right, these results will instantly agree. Which is really troublesome, especially when you think about, you know, how does that jive with our concept of the speed of light? So we're saying, like, but, you know, max speed is, you know, c equals delta d over delta t. You know, they're talking about supposed to be, you know, a max speed of 3.0 times 10 to the 8. But you can't have that and have agreement instantly across the entire universe. They've very, very successfully proven that this exists. They have like an observatory in Hawaii and another one somewhere else in the world, and they can demonstrate that these two particles are quantum entangled. It's a real thing. Just why and how it works is the question, right? So the transactional interpretation has a possible solution where it's like, okay, when you look at this particle, then it goes like backwards in time and says for what this one to be, and then this one goes forwards in time I don't know how to draw it here, but then this one goes forward, so this is backwards in time. Right, communicates with this one of what spin I'm going to be, and so then this one says, oh, okay, I'll go forwards in time and match up instantly and have that same spin. So there's like a link between these particles that's on the time scale, not what we're used to. But the transactional interpretation, once they realize like, oh, wait a minute, well, there's these negative times, we could make use of that in terms of quantum entanglement. So that's what that's about. If you hear about quantum entanglement, like I said, it's a real thing. It's very experimentally observable. Not observable in everyday life, but very much in experiments with electrons and protons and even like buckyballs and things like that. So the leading interpretation and all the weirdness is the so-called Copenhagen interpretation, and it's the one that says that all of the states exist, all of the possibilities exist. The electron, there's a state in which it goes through one slit, there's a state in which it goes through the other slit. When the particle arrives at the screen, the two possible quantum states, collapse, they combine, and one of them becomes the reality that you observe. So these two states all exist. It kind of relates back to this many world thing, I would say. There's subtle differences, but there's similarities for sure. In this one, we're talking about until an observation is made. The observation is that subtle difference between the two. That observing is a key part of this interpretation. So that's when all of the possible states collapse, right, except the one that you observe. And this unfortunately is just based on good experiments. There are tons of experiments that show that quantum particles do this. Okay. So the consequence of that, if everyday life behaved the way quantum particles are observed to behave, okay, this is good experiments here. Like this is actually how quantum particles behave. Okay, that they do this. That would mean that if you had a cat in a box, this is the classic thought experiment that people describe to do with Schrodinger's wave equations and the Copenhagen interpretation. So it's meant to show how strange quantum mechanics is. And we're not saying that real life behaves like this, right? But according to the quantum Copenhagen interpretation, particles are in superpositions of states, meaning that until observed, right, they're not really in either state, but instead of some sort of like limbo between the two. So you've got a cat in a box, right? And it has a Geiger counter with a hammer and a small amount of radioactive material. So there's some sort of vile toxic substance in there, and if the atom inside there radioactively decays, then it releases the hammer and kills the cat. Okay? I don't know why they have to be so dark and gruesome with this analogy, but you could just feed the cat if you want. You look later on and the cat has either been fed or it hasn't been fed. That'd be less gruesome. But to make it interesting, I guess that's just the way they decided to go. Since according to quantum mechanics interpretations, atoms exist in a superposition between decayed and not decayed until observed. Okay, so that until the moment you open the box, right? The cat is actually going to be, as a result of the atom being in a superposition of states, the cat will be in a superposition of states where it is both dead and alive. Okay, so until we look, it doesn't have an actual reality. It's dead and alive basically until you observe. So You're saying the cat is neither dead or alive, but in some sort of state in between the two. Yep, that's the basic idea, more or less. So Schrodinger figured out how to use the power of quantum mechanics to make zombie cats. Oh my God. You'd be like, no, that's not exactly what I was saying. And then there's the zombie cat. But the point is, of course, cats don't behave like this. No one's saying they do, or ever would. But subatomic particles actually do behave like this, which is bizarre. So yeah, hopefully that helps you take you one step further in achieving complete lack of understanding of quantum mechanics, because that's really what you need to have. Once you understand quantum mechanics, you're like, okay, so good. I'm completely confused about quantum mechanics now. I'm done, or I'm gonna look into it further, of course. But that's, you know, if you're not confused about quantum mechanics, you don't understand it well enough yet. Is the saying. So here's Schrodinger. He's wanted dead and alive. Get it? It's a joke. Do you know in quantum physics you can alter the characteristics of the smallest particles just by looking at them? If you say so. I think some girls are just like that. I don't know if this one looks. I don't know. This is. No, it's kind of lame. This one's decent though. So Heisenberg and Schrodinger are traveling in a car. They're pulled over by a police officer, and the police officer asks, "Do you know how fast you were going?" And Heisenberg, of course, says, "No, but I know exactly where I am," talking about the Heisenberg uncertainty principle, right? So the officer gets a little suspicious, of course, right? And so he asks to check their trunk, looks inside, and says, says, "Do you know there's a dead cat in your trunk?" And Schrodinger replies, "Well, I do now," right? Because the cat could have been dead or alive. It's a joke. All right. If quantum mechanics hasn't profoundly shocked you, then you haven't understood it yet, is the actual quote, I guess. All right. So, as mentioned, the other strange quantum effect that is observed, very, very demonstrable, the measurement disturbance. And so it's a strange detail that's not mentioned in a lot of times because it's, you know, kind of confusing. It gives you even more confusion about it, but eventually we want to get there, right? So, and that's the Copenhagen. It's the evidence that leads to the Copenhagen interpretation. But if you look to see which slit electrons or photons or buckyballs or whatever go through, there's no longer a 50-50 chance, right? And so they're no longer in a superposition of states. It collapses down to going through one of them. And so absolutely, I'll show you a video and pictures and describe the process where I can demonstrate this. Okay, so the Dr. Quantum one again, 338. Is it still running or not? Looks like not. Dr. Quantum though. I feel like maybe we might have overlapped here, but 338 was it? To 455. Yeah, we watched the whole thing, didn't we? 338 till essentially the end. Yeah, we watched that whole thing. Good. So the 746 to 946 though. Challenge of quantum reality. Checking to make sure I got the right stuff here. Challenge of quantum reality. On my files, it's a different timestamp, but that's okay. All right. So 746. So just basically, we watched the 746 part, but we're watching out until 946.
Was that enough of a challenge for you?
Yeah, the world works totally differently than I thought it did.
And there's still so much left to figure out.
Lots of challenges.
Lots of opportunities.
Why was the world made in such a funny way? We don't know the answers yet, but that's what makes science exciting.
I guess that was it. I don't know. Might not be the right timestamp. 1750 to 20 challenge of quantum reality. Let's just see, because that doesn't seem right. Physics videos. Challenge of. Let's see if it's the same part. 1750.
The following in
Researchers in Tübingen in Germany placed measuring devices next to the slits. When they fired electrons at the slits, half of them went through the left slit and half went through the right.
See? Told you. Problem solved.
Not so fast.
When the researchers looked at the screen, something had changed. The interference pattern was gone, replaced by a completely random distribution.
Measuring a system disturbs it, and so even though there's interference there when you're not looking at it, as soon as you look at which slit the electron has come through, it collapses into one of those two possibilities and looks like it's acting like a particle.
Many other experiments have also shown that measuring a quantum object disturbs it. It's as if the quantum world is resisting our attempts to unlock its mysteries.
in classical physics, when you measure something, that object stays the same. We're constantly being measured, and I don't change just because the light is shining on me right now. But in quantum physics, if you shine light on an object, you disturb it inevitably. So in particular, when we try to measure something in quantum physics, then what we're trying to measure will be gone.
So fundamentally, she's referring to the Heisenberg uncertainty principle there, right? You interact with something to measure it. We were looking at all the way out to 2010.
Consider, for example, that you're trying to measure the position of a basketball. If you can use your eyes, the basketball's flying across the room, you can see where it is, and you don't disturb it. But now pretend you were blind, and all you could do was throw, say you had a pile of baseballs there. You're throwing the baseballs at the basketball. Some of them will hit, they'll come back, they'll tell you where it was. But every time they hit, they kick it a little bit, and that ruins the information. And in quantum mechanics, you don't have the option of doing anything other than disturbing the system when you measure it.
So we can't measure electrons or other quantum objects without disturbing them.
That's right.
You still haven't answered my question. What were the electrons actually doing between the source and the screen?
It depends on your interpretation, so we don't totally know.
The recent quantum theory seems so counterintuitive, is that we have been brought upon classical physics.
Physicists have developed a number of mental pictures of what's happening, but there's no agreement about which one's right.
Enough there. So what's the next stuff here? Here we go. So this is to do with how the standard model was developed. So how to make sense of all of the, give you some extra details too about each of the forces of nature and how the equations sequentially were developed. Over the course of the 30s and 40s, theoretical physicists led by Paul Dirac, Wolfgang Pauli, and Schrödinger, Julian Schwinger, and all these people you'll hear of as you go through. Feynman, for sure, huge mathematician. To name a few, struggled relentlessly to find a mathematical formalism capable of dealing with this microscopic osteoporosis, which I had to look up and means noisy, difficult to control. So he's talking about the quantum flux, the particles that are zipping in and out of existence, and trying to make equations that jive with that and make sense, right? So they found that Schrödinger's quantum wave equation was actually only an approximate description of microscopic physics, an approximation that worked extremely well as long as one doesn't probe too deeply into the microscopic frenzy. So Schrödinger's wave equations don't deal well with the quantum fluctuations. But they actually fail if you look down close enough. Okay, the central piece of physics that Schrödinger ignored in his formula of quantum mechanics was special relativity. So this is why it's good that I waited until after to talk about this, as it turns out. Schrödinger's wave equations aren't relativistic. They don't accommodate for relativity the way they were originally formulated. He tried to incorporate special relativity initially, but the quantum equation, which this led to, made predictions that weren't experimentally confirmed. So it inspired Schrödinger to adopt the time-honored tradition of divide and conquer. rather than trying through one leap to answer all the world's questions. You know, you can just basically work on one part that is working and keep going and see what it leads to, right? So Schrodinger sought and found a mathematical framework encompassing the extremely discoverable, experimentally discovered, but it was extremely discoverable. You can see it in a physics class, wave-particle duality. But he did not, at the early stage of understanding, incorporate special relativity. So physicists soon realized that special relativity was central to a proper quantum mechanical framework. These two realms should coexist. And this is because the microscopic frenzy that requires that we recognize that energy can manifest itself in a huge variety of ways, a notion that comes from special relativity and E equals mc squared. By ignoring special relativity, Schrodinger's approach ignored the malleability of matter, energy, and motion. So it wasn't complete. So they didn't include the relativity stuff. He tried to incorporate it, but it didn't work. Just a little summary here. Instead, he just basically used the experimental results to work backwards and develop the equations, but didn't really know why they were working. He just basically worked backwards to find stuff that did work, right? So at very small scales, these many virtual particles we've seen, and the connection to relativistic mass becomes a factor, and his equations fail. It leads to infinite energy predictions and infinite probability predictions. The particle has an infinite chance of being at all locations. Be like, yeah, that's just not logical. So the fix. Physicists focused their initial path-breaking efforts to merge special relativity with quantum concepts on the electromagnetic force and its interactions with matter. Through a series of inspirational developments, they created quantum electrodynamics. So Maxwell's equations of electrodynamics, they created quantum electrodynamics. This is an example of what has come to be called a relativistic quantum field theory, okay, or a quantum field theory for short. It's quantum because of all the probabilistic and uncertainty issues that are incorporated from the outset. It's a field theory because it merges the quantum principles into a previous classical notion of a force field. So the electromagnetic equations of Maxwell's were originally just purely wave ideas, electromagnetic waves, right? So they incorporated the idea of random probabilities for particles into that wave theory and made a relativistic, in fact, quantum field theory. So they incorporated special relativity, quantum mechanics, and the wave stuff. And so that was, of course, in the magnetic field stuff, right? So, and finally, it's relativistic because special relativity is also incorporated from the outset. It says if you'd like a visual metaphor for a quantum field, you can pretty much invoke the image of a classical field, say as an ocean of invisible field lines permeating space, right? But you should refine the image in two ways. First, you should envision a quantum field as being composed of particulate ingredients like photons for an electromagnetic field. So we're talking about the exchange particles at this point. Second, you should imagine energy in the form of particles' masses and their motion endlessly shifting back and forth from one quantum field to another as they continually vibrate through space-time. That's the special relativity part being incorporated. So quantum electrodynamics is arguably the most precise theory of nature and phenomenon ever advanced. It's incredible. It works so well, and it encompasses these three branches of theories together. It's just amazing. It says that an illustration of its precision can be found in the work of this person, a particle physicist in Cornell, who's over the last 30 years painstakingly used quantum electrodynamics to calculate certain detailed properties of electrons, right? So thousands of pages of calculations requiring the most powerful computers in the world to complete, but the effort's been worth it. The calculations lead to predictions about electrons that have been experimentally verified to an accuracy of better than 1 part in a billion. Like when you calculate with quantum electrodynamics, your predictions are so reliable, really like the only chance of it being proven wrong would be like 1 in a billion at this point. Absolutely astonishing agreement, of course, between abstract theoretical calculation, the special relativity, the quantum world, and the wave theory all combined. Through quantum electrodynamics, physicists have been able to solidify the role of photons as the smallest bundles of light to reveal their interactions with electrically charged particles such as electrons in a mathematically complete, predictive, and convincing framework. It is quite an achievement. Okay, so this is just a summary of that. The quantum electrodynamics, the three different realms combined. So the success of quantum electrodynamics inspired other physicists in the 60s and 70s to say, hey, that seemed like a good idea. Let's see if we can do that for the weak force, the strong force, and the gravity force, right? So for the weak and the strong forces, this turned out to be amazing. The analogy with quantum electrodynamics, in analogy with the physicists were able to construct quantum field theories for the strong and the weak forces called quantum chromodynamics and quantum electroweak theory. So the quantum chromo is for strong. They could have called it quantum strong dynamics, but they have colors as, like when we talk about an electron has a positive, or in electromagnetism, there's positive and negative charge. And we talked about, different types. There's different flavors. There's the strange and charmed and so on for neutrinos. They just need names, right? And so they ended up using colors as names for different options in quantum chromodynamics for the strong theory, strong force. And so they call it quantum chromo because they used colors. So there's red, green, and blue. So that's why they call it quantum chromodynamics. But yeah, and then the other hand, the electroweak summarizes an important milestone where they realized that the electromagnetism force and the weak nuclear force are actually one and the same. They're actually part of the same thing. So originally we had electricity and magnetism were separate, and they became part of the same coherent framework. And then we had separate from that the weak nuclear force, which is to do with radioactivity, to do with nucleuses. And now on a in a mathematical framework, they're describing all three of those things together now, and that's the electroweak theory. So through their Nobel Prize winning work, Sheldon Glasgow, Abdus Salam, and Steven Weinberg showed that the weak and electromagnetic forces are naturally united by their quantum field theoretical description, even though their manifestations seem to be utterly distinct in the world around us. After all, the weak force field diminishes to almost nothing on all but subatomic scales. It's a force that exists within the nucleus. Whereas the electromagnetic fields, visible light, radio waves, and so on, have an indisputable macroscopic presence. They have infinite field distance effect or influence. So nevertheless, they showed, in essence, that at high enough energy and temperature, such as what occurred near the time of the Big Bang, the electromagnetic and the weak force fields dissolve and become one another. They take on indistinguishable characteristics. They're part of the same coherent framework called the electroweak fields. As the temperature drops, of course, they separate out into these apparently different phenomenon, but fundamentally they're actually one and the same, and the equations work amazing. So if you're keeping score, it says by the 1970s, physicists had developed a sensible and a successful quantum mechanical description of three of the forces, the strong, the weak, and the electromagnetic, right? They had shown that two of the three, the weak and the electromagnetic, actually share a common origin, the electroweak force. During the past 2 decades, physicists have subjected this quantum mechanical treatment of the three non-gravitational forces as they act among themselves and matter particles introduced chapter 1 to an enormous amount of experimental scrutiny. The theory has met all such challenges with aplomb. Aplomb means self-confidence or assurance. I had to look it up. So it's just working amazing, as I've said. Once experimentalists measure some 19 parameters, the masses and so on, the forces and so on. That's the standard model. We're talking about all of the gluons and the vector bosons and so on. They put those numbers into the quantum field theories of matter particles, of the strong, weak, and electromagnetic forces and so on. The subsequent predictions of the theory regarding the microscopic cosmos or whatever, microcosmos, agree spectacular with experimental results. Nothing has been wrong for 100 years. Every time they're like, oh, I predict this is going to happen. Yep, it happens. So this is true up to energies capable of pulverizing matter into bits as small as a billionth of a meter. So it's quantum compatible. It's all good. The current technological limit that we've gotten to, everything's been confirmed. Okay, they keep building bigger and bigger particle accelerators so they can test the theory even further to see if it still holds true. So far it has. For this reason, physicists call the theory of the three non-gravitational forces and the three families of matter particles the standard theory, the standard model. So that's what we were talking about. We were talking about the standard model. It's all the details of those quantum, relativistic quantum mechanical wave theories for the three forces of nature. So this is just the summary page to do with that. RQFT used relativistic quantum field theory, right? So quantum electrodynamics was amazing. So they're like, hey, let's do that for the rest of them. They made quantum chromodynamics for the strong force and the electroweak for the electromagnetic and weak force. So, of course, I have a sneeze coming here, but of course they noticed, something's missing. Oh, excuse me. What about gravity? This is one of my favorite slides, by the way, in grade 12 physics. So what about gravity? The next logical step, of course, is to develop a relativistic quantum field theory for gravity. The problem, as previously discussed, is that Einstein's theory of general relativity is fundamentally incompatible with quantum mechanics. The quantum fluctuations, it embodies infinite energies and so on. So far, no one has been able to do this, right? So just a small homework assignment for you: develop a relativistic quantum field theory for gravity. And then, when you get your PhD, just mention me kindly in your speech. All right. So I should add in gravity. So that'd be pretty cool, right? So get working on that. Let me know how it goes. It's not impossible. Go to university, get a PhD, keep changing. I've modified these files, but I didn't modify the dates from them apparently. So here we go. Last bit. Okay, it's just a neat experimental observation. It's the high school classroom evidence that we can actually see. It took a little bit to put this together, but it worked. So I was happy of the observation effect, and even actually they call it a delayed choice. It's kind of neat. But remember, the Copenhagen interpretation states that measurements change the quantum system, right? So demo number 1 is the measurement disturbance. So we'll show that looking to see which slit it goes through changes the results. Demo number 2 is even weirder, where it's like, okay, the delayed choice experiment, where we can actually send photons through 2 slits and make it so that we have the option later on of determining which slit they went through. So you're going to think of the photons as going through the slits and basically, acting as if they're going to interfere and produce an interference pattern, like they had the chance of going through both slits for, let's say, 5 meters across the room. And then we can measure later on which one they went through. And if we do that, the interference pattern disappears. So you don't have to check to see which slit they went through before they go through the slit. You can actually look after, like kilometers after, if you want. Okay, so this is the apparatus. So yeah, which slit does it go through? What happens if you look through both? So just some notes about this, but the description is like, direct a laser pointer at a screen at least 6 meters away. 12 is better. The further, the better, right? So I went from like the Windows side of 124 all the way to like the classroom door, however many meters that is, probably close to the 12. So you see a bright spot with interference around it, and it's just the laser beam landing on the door. Okay, so we send the laser through 2 slits. Right, and of course you'd see a double slit interference pattern. Okay, so this is the central double width maximum of the double slit interference pattern. Okay, so that's what we're going to be focusing on. We're going to see the interference in that central double slit maximum. So of course the wave model of light and the particle model of light and the quantum mechanical model of light, we're talking about, based on the wave model, we're saying, well, if it's a wave, it's just producing an interference pattern like normal. If it's a particle model of light, you have to sort of say, okay, well, the particle went through both slits somehow. And then the quantum mechanical interpretation would be the idea that, it could go through one or the other or both, or a superposition of states and all this stuff, right? So here's those answers, right? We have the, of course, the wave pattern. The particle model actually, I'm supposed to have said that it can't explain this, of course. True particles can't do this. There's no reason for interference patterns at all with particles. The quantum model, though, says, the particle can go through one or the other or both and so on. and produce interference patterns because they have wave-particle duality, which is the key part of the quantum world. Right? So we've got a double slit laser shining through it. So this is the setup here. We've got a laser shining through it, the double slits. This is a diffraction grating here, and so these are a bunch of double slits. You can actually see the two slits there, and then they get narrower and narrower and narrower. But this one's sufficient for what we do. And so that's what the apparatus looks like. So of course, here's the pattern you see, right? The double slit interference pattern, just like you saw. Well, we saw the single slit interference pattern here live, but on the lesson when we did the video of that, Kayla helped out. So that's the double slit interference pattern. We've got interference, destructive interference throughout this double wide central pattern. So what we do next is we tape a polarizing filter, vertical and horizontal, so that it's horizontal polarization on one slit, vertical polarization on the other. Okay, and that's of course so that we can see later on, we can detect which slit the light went through. So if we do that, the interference pattern disappears because it gives us the opportunity to look and see which one it goes through, right? So the quantum mechanical explanation for this is that the two paths are no longer equivalent. So photons don't behave as if they could have gone through either slit, so they don't interfere. The measurement changes the result. So our measurement allows us to distinguish between the two slits as to which one it went through. And so instead of acting like a wave, it acts as a particle, is what this is interpreted as. And so this is the, so you can see it for yourself. This is the polarizing filters taped on either side of the slit. And here is the resulting pattern on the wall, on the door across the room, right? There's the week before we had interference in bands in there. Now that we're looking to see which slit they go through, because of polarization properties, no interference in the middle. Okay, so that's the measurement disturbance just by polarizing, and so now we know polarizing, vertically polarized light went through left and horizontal went through the right, or whatever, vice versa, whichever it was. We know which slit they've gone through. We could check, and so the interference pattern disappears, which is bizarre. So looking to see which slit they go through destroys the interference. And it's like this guy here, you gotta love him, right? It's like, but wait, there's more, right? As if this isn't weird enough in the first place, there's more. So it turns out if you put another polarizing filter, 45 degrees between the two. So the horizontal one only lets horizontal through, the vertical one only lets vertical through. If you put those together, nothing gets through. In class, if I had the filters nearby, I'd be able to slide a diagonal filter in between the two, and you'd see that 50% of the light gets through. Okay, actually 50 from here. I think it's 25% from that one. But either way, if I put that in place, then 50% of the light goes through. So what happens is, in fact, actually, you don't even need the 3 filters for this analogy. It's just basically from the left slit, we've got 50% chance of getting through. From the right slit, 50% chance of getting through. And so putting the where we go, yeah. So when you first look at this page, the 45 degree filter is not in line. There's no interference pattern, right? So we've got no interference because the 45 degree filter is not in line with the pattern. So we can tell which slit they went through right now. So there's no interference. So I made this page to be able to illustrate what happens. And so here, if I pull that 45 degree filter down in line with the laser beam, what happens is interference comes back. So again, here you could think of the photons as saying like, oh, they can tell which one I went through, so I don't have a 50-50 chance anymore, and so I'm not going to interfere, right? However that works. Then 6 meters later, on the other side of room 124, we say, aha, we can check now to see which one you really went through. We can't check anymore because now we've got a 50-50 chance of having gone through either slit, because this one's on an angle, and the freaking interference pattern comes back. This is like real stuff. This happens in room 124. The video I'll show you shows it, right? But the interference pattern comes back way later on across the room. So realize the significance of this, right? The standard interpretation of the slits being blocked, or you can check to see which one they go through. is thought of as forcing the photons to give up their wave properties. Right? It's thought that observing which slit they go through forces the interference pattern to disappear. Right? But now, sometime later on, after this act of observing has made the wave properties disappear, we can put a 45-degree polarizer back in the mix and bring back the wave property. So you could think of maybe the idea of needing to be able to travel backwards in time to make this logical. The transactional interpretation might be needed here, right? Across the room, on the other side of the room here, I'm bringing a filter in, and it's like, okay, so the electrons at that point have to go back and say, oh, wait, never mind, we've got a 50-50 chance. Let's do the wave thing, guys, or everybody, and then they act as a wave at that point. It is just weird stuff. Okay, it's a wave and a particle. It's a wave or a particle. It's somehow the photons are able to go back in time and change their mind about whether or not they went through both slits or not, I guess, without being able to be determined which one they went through, right? So the wave particle properties had been given up, but then they go back and now they're not given up. So the choice about whether there's interference or not can be delayed. This is the delayed choice experiment. It's pretty odd, right? So does the photon go through one slit or both? As we've seen in demonstrations, you get an interference if you can't tell which has been followed. So we set it up so you could tell, so the interference pattern disappeared. But then, go back in time here and see it come back in place, right? The polarizer restores that pattern. So the video, the results, I put it onto the YouTube for us. The YouTube, get it? That's what old people say. On the Facebook and the YouTube. Anyway, so right here, we've got the interference, sorry, the middle section where there isn't interference, destructive interference sections, because it's the 50-50 chance of having gone through, because we're looking to see which one it goes through. We made the destructive interference bands disappear. You're going to see me move the 45-degree polarizer in line with this, and then that restores the 50-50 chance. So these photons arriving at the screen have to kind of like conspire, it's like, oh wait, we can have gone through either now, even though we're 6 meters before that in space and time. We were locked into having gone through one or the other, and we didn't have an interference pattern. So no interference pattern, and after the fact, you'll see it here. Once I rotate the thing 45 degrees, might have to go full screen here, or load up my normal cancel. Darn it. Can never get YouTube to work properly. Here we go. So there's the no interference. And then when you twist it, the resolution has declined by putting it on YouTube. I will grab my actual file. So it's called coming back. Interference pattern coming back. Should be better here. I just looked at it yesterday. Why wouldn't it be? So there's the no interference, and then see the subtle little interference patterns there. So if I pause right there, you can see dark bands. That's the interference pattern coming back. That's the delayed choice. Weird, wild stuff. So all these little experiments took a lot to sort of put together, but pretty neat to be able to see it firsthand. So single slit pattern at first, because we know which one it went through. Then the 45-degree polarizer later on, right, returns that double slit interference pattern. So this is just a summary page, right? Delayed choice. When the light went through the slits, it noticed it was being watched. So the interference pattern disappeared. That's weird enough on its own, right? Then it travels several meters, not interfering, right? Travels several meters across the room saying, okay, we're not interfering. We're just going to land as a single slit pattern. But then the polarizing filter restores the fact that the photons could have gone through either slit. So, you'd think real tangible particles like photons would have destructively interfered or not destructively interfered at the double slit, right? But that reality would be fixed, and irreversible. But it's not. It's very weird. It's quantum. So this is just videos of the delayed choice thing as well. Delayed choice quantum eraser. So let's check that one out. Delayed choice. Which one is this one? We already saw it anyways, but sometimes it's...
This is a double slit experiment. And I'll show you why it
so this one's a little dry.
Distance slits.
Eventually he does show
exactly what slit is equivalent, so it's easy for you to fire. Put that in the computer. Take.
Yeah, I don't think we want to follow that one for now. I think this one might be a little more last day of school speed.
And here we are, the granddaddy of all, radiate out of many matter.
Anyways,
create an that physicists
time itself.
Nope.
This is not an interference pattern of many.
Just have to skip the first part.
The very act of measuring or observing which slit it went through meant it only went through one, not both.
So in our experiment in room 124 would just be the low polarizing filters there is enough to measure, make the interference pattern disappear.
The electron decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange, never world of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
However, the double hole experiment's mind-boggling conclusions don't end there. In recent years, technology has allowed scientists to perform a fascinating variation of the test. Its results call into question our perception of time itself.
This is like a high-tech version of the double hole experiment. Electrons are being fired toward a barrier with two holes in it. But the scientists can delay their decision about whether to observe the electrons until after they've passed through the holes, but before they hit the screen. It's as though I'm on a baseball field, and there's a baseball being pitched toward the barrier with the holes in it. But my eyes are closed, so it goes through, and it behaves like a wave. But then, at the last second before it hits the screen, I open my eyes and decide to observe it.
At that moment, the electrons, in essence, become particles, and seemingly always were particles from the time they left the electron gun.
So it's as though they went back in time to before they went through the holes and decided to go through one or the other, not through both as they would have had they been behaving like waves. That's really crazy.
That's the enigma. That our choice of what experiment to do determines the prior state of the electron. Somehow or other, we've had an influence on it, which appears to travel backwards in time.
By the transactional interpretation gets talked about.
The experiment begins in the top left corner, with the laser firing two entangled photons either through in the old, so acted in a way actual path information.
That's the details of how the more detailed version actually works. Ours is a homebrew version, but pretty good anyways. And what do we have here? That's just the quantum eraser described more. That was just my timestamps in case I needed it. Polarization, you can tell, is a quantum property since it's to do with this quantum demonstration. So just pointing that out, but whatever. So it's a wave property and a quantum property. Wave particle duality continues. Anyways, that is it. I'm done. We're done. Yay, right? So I'll save and post those things up. I will log off for now, I think, and be available again at 1. I'll set a timer on my phone. Good deal?
Okay, thank you.
You're welcome. I hope you found that kind of weird, because I was intending for it to be. Wasn't clear enough if it wasn't weird. Anyways, yeah, here we go.